We have Siddharth and Patrick up on stage for a talk about how to improve CephFS metadata operations.
Hey guys, I'm Siddharth, and today I'll be talking about how distributed file systems manage their metadata and how they distribute their metadata and how CephFS handles that problem as well. And finally, I'll be giving an overview on ephemeral pinning, which is a new feature we've introduced for CephFS, which we're actually working on. So let me start my talk. So the outline of the talk will be, as I said before, how metadata is handled by a lot of file systems and how CephFS is going to handle that metadata problem. Finally, ephemeral pinning. Jeff and Patrick have already given like an introduction to CephFS, so I'm not going to speak a lot about that, but I'll give you a brief introduction on the components of CephFS. So first off, you have the metadata servers who are doing who handle metadata transactions and who give permissions to clients, etc. And then you have the clients who are trying to do file I/O and trying to do metadata operations as well. And finally, you have the backing object storage called RADOS, which has object storage devices, OSDs in it. So this is the crux of the crux of CephFS would be RADOS, because that is where the storage happens. And so one important question that can arise is, why do we need metadata servers at all? Like, why can't we let RADOS handle your metadata workload as well? This may seem intuitive at first, but that is not exactly the case. So metadata operations, upon an analysis, you can see the metadata operations would take up like almost 50% of your total file system operations. And another thing is that RADOS or storage scales in a linear or straightforward fashion, but that is not exactly the case with metadata. So metadata is fairly complex, and it is hierarchical in nature if you can see the file layout. So it's not very easy to scale it. So it becomes essential to decouple your metadata with your file I/O or storage. So now, since we've established the importance of metadata servers, I'll come to how a lot of distributed file systems handle your metadata. I mean, these are file systems that use metadata servers. So a very common metadata handling strategy is called a pure hashing strategy. So this is employed in file systems like Lustre and ZFS. So what happens here is the client will create a hash of the path name to the file to determine where which MDS the file is going to be. I mean, the inode for that file is going to be. So example for that would be if me, the client, wants to create a file called, I don't know, some file.txt. In that case, I'll have to hash the path to that file. I'll get a hash. Now, keeping that aside, each MDSs would have been delegated a hash range. So you can see MDS1 is delegated that hash range, MDS2 this one, and MDS3 that hash range. Now in that example, you did see that that was the hash value, and that hash value lies in these two values, which is handled by MDS2. So now the client knows that it has to talk to MDS2. Yeah, so that is how a hashing-based strategy works in a brief overview. Now, some advantages you can see with this strategy is that requests are going to be almost evenly distributed across the cluster, since it's going to be a pseudo-random distribution of metadata. So this is fairly obvious. Another advantage you can see is that if the file name is hashed as well, so by that I mean not just the path name, the file name as well. In that case, heavy create activity in a particular directory does not create like a hotspot of load or something like that in a single MDS. So an example for that would be, a simple example is if you have two files under foobar called sid1.txt and sid2.txt, and if you hash them both, obviously it may give two different hashes, so that those two requests are directed towards two different MDSs, and you have a better distribution in this case as well. Now, some disadvantages that you can see in this kind of scheme is that according to, file system traversal semantics, you have to traverse from the root of the directory all the way till the end of the file. So if you have this as an example, foo file.txt, then you'll have to go all the way from the root till file.txt. So yeah, I've just detailed that here. So in this case, we've got that MDS2 is the MDS that the client has to, that offers the client the permissions to read file.txt. And if the client does have the required permissions, then MDS2 will sync with the client to let it talk to Rados directly for file I/O. Yeah. So another disadvantage that, an obvious result of this is that it brings in a lot of inter-MDS hops. So you get hops between MDSs, and this in turn results in a high network overhead. And another disadvantage is that with hashing-based schemes, you lose hierarchical locality. And by this, I mean you lose any metadata locality benefits you get with having like the whole directory tree in the MD cache, because everything is distributed, fairly distributed. Now, another disadvantage that is faced by a lot of file systems, Ceph included, is that renames are expensive. So if you have a case where you have to rename a directory tree, rename a directory in the directory tree which is far up, say abcd file.txt is renamed to fbcd file.txt, and then you'll have to recompute all of the hashes all over again. So this is going to cost in terms of penalty, in terms of performance penalty. Another strategy, which I'm not going to go into too much detail, is lazy hybrid. So lazy hybrid, this strategy works similar to a hashing-based strategy, but it's different in such a manner that you don't have to hash each part of the path name. You can directly hash the full path, and when the request reaches the particular MDS, there is an access control list in that MDS for that particular file, which stores the effective permissions. So you just need to check that. So this kind of implicitly solves the costly problem of traversing between MDSs. Disadvantage is that, like hashing, you lose hierarchical locality. There's no locality benefits in this case. Another disadvantage is that for renames and for permission changes, you will have to traverse the whole path all over again, and that's going to be expensive, even though those operations are pretty infrequent. And finally, this is not exactly POSIX compliant, because you're going to have problems with distributed locking and such. Now we're coming to something close to how Ceph implements. It's called subtree partitioning. Now in subtree partitioning, subtrees of the directory hierarchy are assigned to individual MDSs. So in this case, you can see that, so just to note, the shaded ones are directories and the unshaded ones are files. So here, the orange subtree, you can see that it's assigned to MDS2, the gray one is assigned to MDS0, and so on. So subtree partitioning, with subtree partitioning, you can get like a linear growth of your metadata cache along with a number of MDSs, and that's pretty beneficial. And also your cache utilization will increase due to your spatial locality increases. Now, some fairly obvious advantages you can see is that here you have good hierarchical locality. So since you are storing, not exactly storing, since you're caching entire subtrees in the RAM, you don't have to traverse from MDS to MDS in this case. So you have that benefit. Next one is it scales horizontally. So along with increasing number of MDSs, you can assign subtrees to it, and you can get a fairly horizontal scaling in this case. Another advantage is renames are not as expensive as hashing-based distributions, because here if you're modifying the directory tree, you don't have to hop from MDS to MDS. You can do it locally within the metadata cache of the same MDS alone. But you're still going to have problems with renames, which I'm not going to get into. So all this considered, your naive subtree partitioning seems like a good choice of a metadata management strategy for CephFS, but that's not exactly the case. You still have a few problems here. So one problem is that this does scale in breadth, but not exactly so well when you try to scale it in depth, because when the workload grows in depth, you're still going to have a hotspot of activity on that particular MDS. Or if it happens on multiple MDSs, then obviously you're going to have multiple hotspots, which is not exactly good. And you may have MDSs which are non-busy, and those compute resources are effectively wasted in this case. So we've come up. So CephFS uses something a more dynamic version of subtree partitioning called dynamic subtree partitioning. So we've the problems I've talked about before can be mitigated with using a balancer, using a metadata balancer that can export subtrees from one MDS to another based on the load factor or how much activity is going on in that particular subtree or portion of the directory hierarchy. This can be achieved using a metadata counter. So whenever you have activity going on that particular inode or seeder, then your metadata counter increments, and based on that counter, your balancer is going to decide whether you need to export it to a different MDS or not. So since you're not explicitly storing metadata, it's not really difficult to migrate it between metadata servers. So migrating between caches is not that difficult. Even when I said this, there are cases where you have a performance penalty rather than a performance boon. On some workloads, you have excessive migrations, which is definitely not good. So CephFS does give the option to override the metadata balancer by allowing the cluster admin to manually pin the subtrees. So in cases where the metadata balancer is not working well, the cluster admin can choose to decide to pin that subtree to a particular MDS as he chooses. But even the option of giving the option of pinning subtrees to the cluster admin is not exactly foolproof, because you can't exactly decide how the workload is going to be, and if you can't exactly gauge the knowledge of the cluster admin to decide where he's going to pin the subtrees, which MDS is he going to choose. So to mitigate and automate that process, we've come up with something called ephemeral pinning. So this is a metadata distribution strategy using consistent hashing as its core. So so we've decided to use why consistent hashing. Actually, why hashing in its sense is because you can get a proper distribution of metadata if you use hashing, and you're not hashing independent directories in this case. You're hashing subtrees. So I'll talk about that later. When I'm explaining this, you might find it difficult to understand. I have diagrams that explain it properly. So just hold on. And so to achieve this, we've come up with two export pins, two exaters in distributed file system sense. So these are export ephemeral distributed and export ephemeral random. So the cluster admin can choose to set either one of the exaters on directory inodes based on knowledge of a portion of the workload, of how the file layout or the workload is going to be. So if you have a fairly distributed workload, in the sense that the workload is creating a lot of directories under a single parent directory, in that case you can choose to go for export ephemeral distributed. And when you have a fairly a workload where it grows in depth, then you can choose to go for export ephemeral random. And setting this exater is going to override the metadata balancer for that particular subtree. So I'll give you a brief explanation on this. Don't worry if you can't understand it. I hope the diagrams would make you understand it. So export ephemeral distributed, if you set export ephemeral distributed on a directory, then all the child directories or the child subtrees are going to get distributed across MDSs using a consistent hashing strategy. The hashing is done on the inode number of the child directory. Export ephemeral random is a bit different from export ephemeral distributed in the sense that you're doing this hierarchically. So when you set this on a directory, the whole subtree or the subtrees that are getting loaded, which are nested beneath it, will get distributed to random MDSs probabilistically, and you usually set the value of the exactor. It's worthy to note that the value of the exactor is the probability that I just mentioned. So, and we usually make this probability as low as possible. I'll explain this in the slides. So this is export ephemeral distributed. So that is a parent directory that exists in MDS1, and you have set the distributed pin on it. Now, when the workload is generating directories under this parent directory, the hashing is done and metadata is distributed almost pseudo-randomly across the MDSs. So as you can see, for a fairly distributed breadth-wise scaling workload, I mean, knowing this, it would help in setting the value of the exactor and scaling metadata optimally in this case. So this is a fairly very small workload to kind of gauge how the inode distribution was across 3 MDSs. So it was a very small workload, didn't even take a minute to run. So you can see that how the distribution, how the metadata is distributed almost perfectly across the 3 MDSs. So this is using the export ephemeral distributed pin. Now export ephemeral random is different in the sense that okay, you have the parent directory first. One thing to note is that whatever is not getting pinned and hashed, it is assumed that it's going to MDS1. So now it's assumed that parent directory is in MDS1 and directory 1 is in MDS1. And whatever is getting hashed, you can see that goes to different directories. So directory 2 is not getting hashed. This is not happening because I told that it's probabilistically getting pinned, right? So how you do it probabilistically is you have a random number generator to generate a number, and you check whether it's greater than that particular probability that you set. So in this case, that is not happening. So now you can see that directory tree, the condition satisfies and it goes to MDS2. Not happening. Directory 6. So if you have a fairly depth-wise workload, then this can work really well in that case. So finally, let me talk about why we're using consistent hashing. And okay, to say that, let me say what is consistent hashing first. So consistent hashing is basically a distributed hash table scheme, but unlike a naive distributed hash table, you don't have to resize the entire hash table when you have cluster modifications, like when you're scaling out or when you're scaling down. So CephFS has this another added advantage that you don't need to store all the data structures of consistent hashing in your memory, because your ranks are arranged in an ascending order of number. So you have if you have 3 MDSs, say MDS A, MDS B, and MDS C, then you're going to have an implicit rank for each MDS called the MDS A is going to have rank 0, MDS B is going to have rank 1, and MDS C is going to have rank 2. So having that kind of negates the need to store data structures in your memory cache. And yeah, that's it. Ephemeral pinning is a work on progress. You guys can check it out in this link. I still have a lot of benchmarking to do, probably a lot of request distributions, and check that out probably. And yeah, that's it. This is my mail. If you have any doubts, you can ask that. Time for questions. Okay, no questions. That's good. Yeah,
Thanks
thank
a
you.
lot.
Yeah.